The first speaker will be Ying-Jer Kao. Ying-Jer has worked on very broad different applications of tensor networks over the years, and he's always had very good taste, I would say, and like what's most interesting. So he's going to be telling us about solving time-dependent PDEs with projector-splitting integrator.
Okay, thanks, Miles. And first, I would like to thank the organizer for this opportunity to come to Grenoble again. And if you're careful, then you notice I changed my title. So out of respect to our Christian and the mathematician in the audience. But I might slip the tongue, still say TTVP, but bear with me. I try my best. Okay. So this work is actually it's done with my my PhD student Hao-Ti Hong. The goal of this talk is actually very simple. I look at this equation and I start to learn from Miles about this QTT thing. And so I look at this equation and I say, okay, let's represent this function as MPS and use QTT to represent the Laplacian as an MPO. And then use our program, TDVP, PSI. Okay. PSI is a projector-splitting integrator algorithm to perform a time evolution. So we have the code, everything is ready, so let's run it. Okay, so that's basically my talk. And so if you look at it, this is sort of like the time evolution of MPS that most physicists know very well. So you have some operator you can write in terms of MPO, and you evolve it and you project it back to this MPS manifold, and then into time evolution. Okay, so that's what we started out to do. So this is a reminder of how you do time evolution in this MPS manifold. So for the sake of simplicity, I still stick with the Schrödinger equation for now. So imagine I have a Schrödinger equation. I have a Hamiltonian. I want to find a time evolution of this wave function. And so if I want to restrict myself, this wave function as an MPS. So basically, I want you to, so this is a uniform MPS, but the idea is the same. I want to parameterize this wave function using some matrices. And these matrices can have time dependence. So then naturally, there are two questions. The first question is, how do you take the time derivative with respect to of this wave function parameterized by this MPS? And another question is that after you do this operation, is this wave function or this output function is still an MPS? So from Christian's talk yesterday, we learned that actually you have to think in terms of this tangent space idea. So you think of this MPS as some kind of manifold, which is spanned by all the possible matrix Roth states for a given bond dimension. And so I have a map from the matrix to this wave function. Okay, so this is a nonlinear map. One example you can think about is that any sum of two MPS it will not go into the same manifold with the same bond dimension. You have to increase your bond dimension, so it lives in another manifold. And I can define a tangent space for a given wave function here, and then with that, I can define a tangent vectors and so that. And all this time evolution then can be sort of understood as this following evolution. So I basically start with a wave function at this MPS manifold. And so I'm trying to propagate along this tangent space of MPS, but this operator will bring me out of this MPS tangent space. Then I need to project it back to the tangent space. So And the way to project it is just to find the MPS such that minimize this this distance of these two wave functions. By doing all this, we got this projected Schrodinger equation. Okay, and so to evolve this, okay, so this is just a notation we're going to use. We're going to use left canonical, right canonical, and so I think many people are familiar with these tensor network diagrams. So this projector-splitter integrator, or this unfortunate misnomer TDVP, is basically how to construct these operators and how to construct this effective Hamiltonian. So you have a single side effective Hamiltonian and zero side effective Hamiltonian. And by doing that, you come up with some equation like this, and then you have an equation for the matrix elements for a given site, and then you can do an integration. Okay, so then you can use your favorite integrator, for example, RK4, to solve this differential equation. So this is pretty much just the scheme in terms of this time revolution of MPS. So we're going to directly apply this. Okay, so I guess I don't need to go into the details, but this is basically, if you have one-dimensional function, then you can do QTT, and so this is a way. So people coming from quantum computing community, they also like this actually. But they want to call it qubit. So this is a qubit representation of the number, and you can write it in this way. So I think there's some confusion occurred yesterday and in the morning, but we're basically saying the same thing. Okay, and the key important thing is actually it's Laplacian. Okay, how do you write Laplacian? And if you don't know how to construct actually, this Laplacian has a very simple MPO representation. Okay, I'm ahead of myself, but but use the finite difference method, and you can write down the Laplacian. You can have an open boundary condition look like this. So it's a tridiagonal a matrix, or your periodic boundary condition. So you have some entries at off diagonal. And so it turns out, well, we all know that any tridiagonal matrix, you have a MPO low rank MPO representation, and this rank is 3. Then here are basically just the explicit construction taken out from this paper. But this is pretty easy that you can work out yourself. So basically, you can write this in terms of identity matrix and raising and lowering Pauli matrices. So we pretty much get everything we need, right? We know how to write the differential operator as an MPO. I know how to encode my initial condition as MPS. I can do TCI or basically do SVD. And then I know how to do the time evolution, okay? So everything runs smoothly. This is the expected solution I get for this heat equation. So that's what we did. So we took our TDV PPSI program and run it. But this is not what we get. Okay, so there's some caveats, okay, for those who want to directly use your code. This is my initial condition, and as soon as I start time evolve it, it got crushed here, and it's centered around here. So what's happening? It turns out I cannot think of this MPS as a wave function. So when I think of this as an MPS wave, as a quantum wave function, each time step I normalize it. So by normalization, I mean that I have a singular value. I do SVD, say here, and then I truncate, and then I have to redistribute my singular values such that I get a norm of my wave function is still 1, such that I have canonical form and so that. Okay, but here you don't have to do it. Okay, you just and by not doing this, there are some caveats at the boundaries. I won't go into detail. So basically, you cannot drop in the old-fashioned way. But with this caveat, then I can run it. And okay, so this is basically after this minor fixes, then I got this heat equation. Okay, so you'll say, okay, so what's the big deal? Okay, that's the same thing that I told myself. So what's the big deal? Okay, so then we start thinking, okay, maybe 2D is more interesting, and 2D. So basically, just put your coordinate x, coordinate y. So your quantity look like this. And then you can construct the Laplacian. And in Cartesian coordinates, this is very simple. You have an x and y differential operators independently. So we know how to do it. It's just a tensor product of my one-dimensional Laplacians. Okay, then I can write on the MPO for this. So do the this should be the Laplacian. So the Laplacian of my function is basically just just contract this two, and this is the thing that we have. Okay, now we want to try something harder. Okay, so basically we can do the same thing. We have a Laplacian, and we have a potential term. So basically, we want to solve GP equations and time dependence of the GP equation, but I can formulate everything in terms of this integrator, okay? And just the only caveat is this nonlinear term, but we know how to deal with. You change the MPS sort of like put it at the diagonal. You have an MPO, then you can do this nonlinear term. Okay, so then we try to solve this, and so this is a Gaussian initial condition. Is the Gaussian at the origin, and the trap is like this. And the reason why you see these stripes is because I'm solving this on the Cartesian grid, and the boundary condition is actually the boundary is 0. So the reason why you see this interference pattern is not because my solution is crazy. It's just because it reflects the boundary condition. Okay, and we can compare with what people did. So this is where I need to ask for help. This is the only reference that we could find. I mean, before, I think there's a recent publication by Xavier and some other people. So this is and I don't think we see many like time dependence, because I thought this is an old problem. People must solve it to a T. But this is what we can compare. Okay. So although the solution looks very similar, but we found that if we do this TDBP, I don't know how they do the integration. There's a time lap. So it's just in terms of this solution, there's a time lap between our solution and their solution. So here is t equal to 5.6, and the solution they show is at 5 seconds. Okay. Again, so yeah. So we don't really have a good reference point. Again, they solve at the t equal to 5. Our solution has to go to 5.6 with the same set of parameters. Okay, so that must be this problem must have a very good numerical solutions. It's just I don't know the reference. Okay, so all this fringes actually puzzled me for a long time, because I said this is spherical symmetric. This is spherical symmetric. why do you have this crazy thing? So I asked my students a lot of time, and then he basically said, okay, this is basically a boundary condition. Okay, I'm saying, okay, let's try to do it in another way, in the polar coordinates. Okay, because if I can, my idea is very simple. If I can respect the symmetry, then my theta direction should be almost just product state, right? I have a very low entanglement entropy. So so that's kind of how we started. Okay, yeah. So so here just a demonstration of if I want to use content to parameterize this function. And if I use the Cartesian coordinate, then this is the what's plotted here on the x-axis, y-axis is the entanglement entropy, and these are just the sites, is y and x. And to get the good error versus the bound dimension, I need to go up to 80 sites, 80 bound dimension 80 to get a very good reasonable error, 10 to the minus 13. But if I observe that there's this sort of like a circular symmetry, then I write my contact as in this way, and you can see that the theta direction, because this is basically a product state, I don't need many digits, and it's all entanglement entropy is 0. Or then I can just focus my resources on the R. And so this is basically, I just need a chi equal 14 to get a similar accuracy. Okay. Yeah. Okay. So this is pretty much the same thing. This is just plotted out what's the function look like. So if I have this kind of symmetry, it's natural to use the right coordinates. Okay, so then we march forward and we want to do okay, solve the PDE. Okay, so from elementary textbook we know how to write Laplacian in polar coordinates, but there's some caveat here. The Laplacian is not well defined at the origin, r equals 0, right? And also you have to be careful. You have to have periodicity. You have PBC along theta, because 0 to 2 pi. Then you have to take care of this. Okay. So this morning we heard talk about using this similar idea, but we were not as smart, so we didn't use Jacobian. We basically do it brute force. Okay. So we write down the final difference operators. The first one is okay. Well, not quite okay, but the first one is like this, and the theta one, because it's a periodic boundary condition, I have off diagonal terms, and my operator, I have this inverse of r and inverse r squared. Okay. So when r goes to 0, then I basically not defined. So how am I doing in time? Okay. 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 So this is the way. It's not undefined. It's not because there's a singularity. It's just the way you define your coordinates. So I won't go through this a lot of details. The first thing is that, okay, I can try to avoid this singularity by make it go away. And the derivative, okay, the derivative, I will just use a Cartesian patch at this origin, such that I can I can just also do the calculation. Okay. So our arguments like this. So not sure it's 100% correct. I mean, the mathematician in the audience might chase me afterwards. But so argument is that this is not a one-to-one mapping. So if I want to use the finite difference, just use patches, just use Cartesian patches to compute this derivative. I can choose these points. I can choose these points. I can choose these points. So in that sense, I'm choosing different data. So our argument is that, okay, maybe to get the right derivative, I need to average over all directions. And so by doing that, it's like you assume locally there's some radial symmetry. Okay. We test this and it seems to work, but I'm not sure that because this singularity is basically just a brush under the carpet. Okay. So with that, we can write down our operators and construct the MPOs. So the key thing is that, okay, it's actually not trivial to write down the MPO for this Laplacian in a periodic boundary condition, but you can do it. So this is an explicit MPO form that, and also we modify our MPO for the R equal to 0 side, so we need to change it. But again, this is easy to write in terms of MPO. Okay, so by fixing all this, then again I can write my Laplacian as an MPO. I have a derivative with respect to R and all these different MPOs, and combined with my projection operator, then I can solve again this. Okay, I forgot to fix this. This is my TDVP equation, but okay. Again, this is a time dependence of your matrix element depends on all these crazy contractions, but this is what we know how to do, and nonlinear terms and so on. Okay, so yeah, then group everything together, then we go back to this. So these are individual terms. There's a single side effective Hamiltonian and the zero side effective Hamiltonian and so on. And then we just do an integrator. Okay, so then with this, we tried to solve this rotating GP equation. So the difference is that I have some term which is give you the finite angular momentum. So in principle, you expect to see vortices to occur. And so we try two different methods. So we start from a random configuration, and we do an imaginary time evolution. Okay, and we use either the direct integrator or TDVP. So tau equals 30 is what we pushed, and you see some difference between these two, and yeah, so we don't know which one is the right answer, because apparently RK4 shouldn't be directly used on this equation, or I don't know. I need a math expert for this. But so this is the results we get either by RK4 direct integrate this equation, or use TDVP right on the TDVP equation and do the integrator. Also, with that, we know we can do quench dynamics, because we know how to do a time evolution. So I can start from a ground state with certain omega. I remind you, omega is the parameter in front of the angular momentum, and quench into some other Hamiltonian, and we can do the time evolution. Yeah, and so far we see this TDVP algorithm give you some fine structure, but we don't know if this is because our bound dimensions is too small. We're using a fixed bound dimension, and maybe there's the error accumulates.
Just change it a little bit. Use a fixed bond dimension. You can repeat the computation with a little bit smaller one and see whether things change. So what happens then?
Yeah, so that we're still starting. We're changing. So this is very fresh. This is from last week. Okay, so we can do some. I think that roughly the evolutions are captured, but there's some fine points that we don't know, and we didn't check any like conservation laws yet. So yeah, so if you know any like a good solver for this GP equation with rotation, then I'd love to benchmark against the state of the art. Yeah.
I think you could use exactly the same finite difference stencil that you're compressing with a tensor network and just solve it without a tensor network.
Okay. Yeah, that's a good point. Yes. Okay, so that's pretty much what I want to tell you today. So we basically implement this algorithm to solve time-dependent PDE. By construction, we develop explicit QTE representation Laplace operator in polar coordinates. Yeah, so we want to benchmark against state-of-the-art solvers for GP equations, which we still need to do. And after Christian talk, then we probably need to implement the Bach integrator. And also, the origin of this work is actually we want to see if we can capture the emergence of vortices when you start from so you start rotating and maybe the vortices you can use a lower bound dimension because you have a local like circular symmetries near the vortices, and then you can use this method to solve it and patch it with like some global like background condensates. Okay, yeah. So I'm very interested to see if we can combine with the multi-patch method that has been developed, and also I think the interesting is can we generalize easily to the spherical coordinates and how to benchmark it. Yeah, that's it. Thank you.
Okay, we have a lot of time for questions, so thanks, Ying-Jer. Maybe since we have a lot of time, I can ask when to start. So you mentioned you tried DMRG at one point versus versus TDVP, and I can see why the time evolution was easier to work. But did you just try self-consisting the DMRG? Was that also not working?
No, we just have one shot, and we didn't work very hard. So
because I didn't know if maybe you tried self-consisting, but it was like really unstable or something.
You mean this to get a solution? Yeah, we didn't try very hard, but we have the time evolution code, so we basically just use it. And also, I think because Jiaming, I think Jiaming is the person to blame because he told us he tried DMRG, didn't work it, but he has to use the optimization and imaginary time in his work. So we trust him.
Yeah, so maybe it just needs more.
Yeah. I think we should try to get a better bound state. Yeah.
Okay. Just to get the numbers, when you say 5 per flight, it means 5 bits per.
Yeah. So R is 5 bits, and it just.
So it means the total size of the vector is 1,000.
Yep.
So you could actually benchmark with just without QTT at all.
Yeah. Yes.
Okay. But you didn't.
No, I haven't done it yet.
Questions?
Naive, non-expert questions, but I missed a bit the advantage of the TDVP if it's very similar to the RK4 direct in that case. So what's the advantage you're going to get with the TDVP?
So it's just because we have the code, we can.
No, I understand that, but there's no immediate advantage here.
Do you think it could bring more accuracy?
Yeah.
I was hoping that you can bring more accuracy, But looking at this result, I'm not convinced myself. It's not clear yet, but I think this is a better time evolving integrator, I think.
Okay, more questions? Yeah.
Do you have an idea to go from Cartesian coordinates to polar coordinates by, for example, applying MPOs or?
Yeah, I think in this paper they oh, shit. In checks, okay, they figure out how to do it. I think it's in so this paper you can use Laplacians and transform it. Maybe the experts over there.
Thank you very much.
You said the expert is here, so let's give that mic to the expert and he can answer the question.
I'm not sure who that is, who you're talking about. Okay.
DTF.
Yeah, everyone's pointing at us.
So basically, the question is that you guys implement this Jacobian method encoded in terms of NPO, right?
Yes, that's what we did.
Can you comment on that?
On that, yeah. So it's basically what we did. We started from a usual Cartesian grid, and then write down the Jacobians that transform to the polar coordinates, and then use that MPO representation. Just transform all of your operators that you have here from the Cartesian grid to the polar coordinates, and then just run the simulations with those MPOs and corresponding boundary conditions. And what you really have to be careful with is only this region here, where you basically get periodic boundary conditions.
Yeah.
And because we didn't have any issues with the center point, because we always put a cylinder there. So we never had nothing there. So that singularity that one might get was not an issue for us. I can see that might be causing you some trouble.
Kind of comment or question about that, but it's pretty naive. But I wondered if you all thought about this, is that you can encode functions that are like infinite valued, right? Like in this formalism. Like an example would be a delta function. It's like not normalized. But the trick is that you just don't put all the numbers into one tensor. Like you could just, like if I write, 2 times 2 times 2 times 2, I could just save that as a bunch of 2s. And that's diverging exponentially to infinity, but I don't have to I'm not forced to multiply them all together.
Right.
So I wonder if that is useful here at all. Is that kind of trick useful?
So in some of the problems we did, we also had a point source in the middle. And there we did exactly what you said, with a time-dependent point source. And basically, we didn't need to go up to infinity because we have a finite grid size. So we just made sure that all the tensors add up to an area of 1. So yeah, that we do.
Then that might go well if the tensors touch your function one at a time in the algorithms. Things might balance out automatically, where you never have a large number in your computer.
Yeah, we didn't get any problems with it. So it was never really diverging. This was,
Okay.
Yeah, so that's our hunch on this, but I don't know. Basically, we just assume this is smooth, and then we just hide the singularities. But
also, maybe just a comment and highlight. So in TensorTrain community, there were quite a few papers around 2011, 2012, where many different PDEs have been solved. And again, Vladimir Kazeev had a paper on how to represent different operators like Laplace and QTT and others. And we actually had this in toolboxes for quite a long time. I don't remember if we did polar coordinates, but I would say it's sort of rather straightforward to, so something like that. So, but I think the correct reference for the Laplacian is with Kazeev thing.
is it?
Well, it's trivial, I would say. But
This right reference?
Yeah, that's the.
Yeah. So this is who you got our inspiration from.
Yeah. So, but polar coordinates, I would say maybe it's takes probably 1 hour to do. To be honest, with the toolbox. Anyway, it's not so difficult.
Okay, we have time for one more if there was. Otherwise, we can. Okay, let's thank Ying-Jer again.
Cool.